3.7. So again, this is going to be a short 3.7, 3.8, and 3.9, and that will finish this chapter, but we'll just take a test over 3.7 to 3.9. So optimization problems, that's kind of like the related rates problems. We're talking about optimization, so that means we're looking at maxes and mins. What either max optimizes, meaning maximizing, or trying to find out what the smallest is, so minimizing. So either looking for maxes and mins, and so what that is about taking the derivative and setting it equal 0. So it's the same thing you do. So first of all, you have to understand the problem, which I guess that's, I don't know what that's called, but you're not going to totally understand the problem, but try to understand what it's getting at, not necessarily understanding as in understanding how to do it, but just understanding what is it talking about a little bit. Okay, and then to help you understand, you can go ahead and draw a diagram. That might help kind of what's going on. If you have a shape, a circle, a cylinder, maybe you have a rectangle of some sort because you're talking about maximizing a plot of land or something like that, and then introduce your notation. So usually you're going to have some type of formula. When you draw these diagrams, you'll realize that you're after area, or maybe you're after volume. And then so then you can write these equations for volume and area and then introduce your notation. Right? So let's go ahead and look at a couple of examples here. So here we have a farmer and they want to maximize something, probably. So we have 2,400 feet of fencing and want to fence off a rectangular area. So go ahead and draw that rectangular. And the field borders a straight river. So down here we have the river, and so this is a straight river. So that means we don't need fencing along that, right? So that's kind of what I mean by understand the problem. Understand what's going on in the scenario. Not necessarily how to do it, but understand what the problem is kind of asking and what you're talking about. So we need fencing. We don't need fencing along the river. Here's where we need fencing, right? So all this is going to make up that 2,400 feet of fencing. And so we want to know what are the dimensions of the field that gets the largest area. So I use the words here, large area, but most of the time it's going to say like, how can we maximize the area? The area or something like that. So again, that's taking the derivative and setting it equals 0, right? And finding those x's and then plugging those x's back in to our original to figure out which one's the largest, right? So it's the same thing we've been doing, especially finding absolute max and absolute mins. So there's really no difference here. So we just have to kind of figure out, understand what it's talking about with this being 2,400 feet. Well, isn't that the perimeter? So you're going to have to think back to geometry. You know, perimeter equals length plus width, right? 2 length and 2 width normally on a rectangle, but here we don't need the river part, so we can get rid of one of the lengths. So we just need length, width, and a width. So that's 2w plus L. So that's going to get us our perimeter, and then we want to find the largest area. So we're going to use this formula to help us because we know we're using 2,400 of fencing, so it's going to equal this. But then we know for our areas what we want, the formula for area of a rectangle is length times width. So that means if I want to maximize my area, I want to find the derivative of my area, right? And set that equal to 0, and then go ahead and plug that in. So first we only need one variable because here we have length and width, so I can't take the derivative of that because I have 2 different variables. So I need to go ahead and solve for one of these, either length or width. Probably length is easier because I don't have a variable, or don't have a coefficient in front of the length. So if my minus that, my length is equal to 2,400 minus 2w. So I can go ahead and plug that in for my length. So my length is 2,400 minus 2w, and I'm going to times that by my width, right? So now I have, oh, that's just plain area. Now we want to maximize that, so I want to take the derivative of that. So I go ahead and distribute that W in, so then I have 2400 W. I wrote too many. There we go. And then W squared. Okay, so that's what I'm going to take the derivative of, because I want to maximize the area. Now you could do this if you wanted to, just by plugging in numbers and adding up to 2400 and see which one gives you the largest area, right? So I could just start taking and say, okay, length is 1, and this is, my width would be, what? Plug in 1, that would be 23.99, divide that by 2, and so that would be my W. So my length would be 1, and my W, my width, that's an ugly W. My width would be whatever that is divided by 2. And then I can multiply those, right, to figure out what my area is, and I could keep on doing that until I find the maximum amount of area. Well, that would take a while, or maybe not. Maybe you could figure it out pretty quick. I don't know. But the other way is taking the derivative of our area, set it equal to 0, because that's where we're going to find our maxes and mins. Go ahead and solve this so we can divide everything by 4. So we get 600 minus W equals 0, because when I divide this side by 4, I still get W. Or I still get 0, sorry. Alright, then we can just go ahead and say W equals 600. Alright, so now we know our width to get our maximum is 600, and so now we can take our perimeter, which we know to be 2400, and we know that our perimeter was equal to length plus 2W, so I can plug in my W 600, times it by 2, so I get 1200, and if I add my length, I'll know I have 2400, or I can go back. I did it kind of the long way, but we do have this formula right here that said 2400 minus 2W equals our length. I could have just easily put it in there, right? So minus 1200 from 2400, and I get 1200. So our length equals 1200, and our width equals 600. And then, so then I can go ahead and multiply those to get my max area. So my max area with these length and width. So this will give us our max area, I guess. And so 6 times 12 is what? 72. So 72, however many zeros, 4 zeros. So that's our max area if I multiply. Yep, so that's our max area with those dimensions. Okay, so that's kind of how you do these problems. Okay, so here's another one. We have a cylindrical can. So draw it. Cylinder. And it can be made to hold 1 liter of oil. So that's talking about volume. So our volume is 1 liter of oil. And we want to find the dimensions that minimize. So that means taking the derivative. So we're going to take the derivative of our volume. Or wait, let's make sure. Minimize the cost of the metal to manufacture the can. So here we're actually, our derivative is not going to be our derivative of the volume, because we're not maximizing or minimizing the volume. We're minimizing the cost of manufacturing the can. Well, what it's going to take to manufacture the can is the surface area, right? Depending on how big we make the can or how small we make the can. So we want to make the can really, really small, but that can still hold this 1 liter of oil. Okay, so we want to make it small as possible. So we're trying to minimize the size of that can. Well, the size of the can is made up of the surface area of the can. So that would be like if I cut the can right here, it would fold out. I've done this in class before. Maybe a couple years ago I did. Maybe I did last year. And then it's made up of a circle on top and a circle on bottom. So the area would be a rectangle, which if I cut right here and I fold it open, wouldn't the distance of this be the distance around a circle, which is 2 pi r? All right, it's the circumference. And then the length, isn't the length just the height? So there's the length and width for the rectangle of the can, and then we have two circles, and area of a circle is pi r squared, and we just have 2 of them, right? So it's 2 pi r squared. So the area of the rectangle part is going to be, multiply these, 2 pi rh, and then the two circles will be 2 pi r. So my total surface area is 2 pi r h plus the area of the two circles, 2 pi r squared. Okay, so we want to maximize this. Well, again, we have two variables, which kind of makes it a little bit tougher. So that's where we use this volume information that they give us. So volume, if I have 1 liter, that means I have 1,000 cubic centimeters. And why I have to do that too, is because my area is talking about length and width, okay? Where liters is talking about volume, so that's why I kind of have to switch it to centimeters, because my length and my radius is talking about in centimeters. All right, so then we can go ahead and take this, and volume, we know volume is equal to, of a cylinder here, if we can look that up, is 2 pi rh. And so then we can go ahead and start solving for h or r, but it is a squared. 2 pi r squared h is our volume. So now we just want to solve for this. So we have 1,000 equals 2 pi r squared h. So we probably want to solve for h, would be pretty easy. And then we can plug in that h and simplify, or we can do it the other way. It doesn't matter. Here I'll solve for h because I only have one h here, right? Rather than solve for r and have to plug in an r here and an r here into this equation. So if we solve this 1,000 cubic, is it cubic millimeters? I can't remember. Cubic centimeter, I think it's cubic centimeters. This is 1 liter. Okay, equals 2 pi r squared h. So if I just divide by pi r squared, or 2 pi r squared, I get my h. So I can start reducing this. That'd be 500 over divided by pi r squared. So then I can plug it into my surface area, 2 pi r, and then my h, which is 500 over pi r squared plus 2 pi r squared. Okay, now we can simplify. These r's would cancel. I'd still have 1 on bottom. The pi's would cancel, and 2 times 500 is 1,000. So I have 1,000 over r plus 2 pi r squared is our surface area. And then, of course, I had to mess up because it's not 2 pi r squared h. That's not volume. It is just pi r squared h. So now you're yelling at me because I did that. So that stays at 1,000 on top. Okay, and so this would become 2,000. Okay, so now I want to rewrite this as just exponents, as everything in the numerator, right? So then I can derive this easier. So now we want to derive that. So, because we want to minimize, so that means we're going to take the derivative and set it equal to 0. So that would be negative 2,000 r to the negative 2 plus 4 pi r. We're going to set that equal to 0. And then since these both have r's in it, we can factor out an r. But I want to factor out the smallest r, so I want to factor out an r to the negative 2. So r to the negative 2. And I could probably factor out a 4 as well, right? So that would be negative 500. No more r's because the r squared, r to the negative 2 would cancel. And then here, when I divide by r to the negative 2, it's going to be an r cubed. Oh, that 4's gone. I factored that out. Okay, and that's set equal to 0. So then we can set each of those equal to 0. So 4 r to the negative 2 equals 0, and then negative 500 plus pi r cubed equals 0. So this one, r equals 0, which can't have a radius of 0. We don't have a can. So that's not going to work. Then we can solve this one. So r cubed equals, add 500 to both sides, divide by pi, and then we're going to cube root it. So we need our radius to be the cube root of 500 over pi, whatever that is. Then I can find, because I want my dimensions, right? So this is what's going to minimize the cost. This r is going to be the smallest radius we can have to fit 1 liter of oil in this. And then we need our h, which we already have. Our h is 1,000 over pi r squared. So our h is 1,000 over pi r squared. So now I can plug in my r right here and square it. So that means I'm taking the cube root of 500 over pi and squaring it, timesing that by pi, and putting that 1,000 on top of that. That's my h. So simplifying here. So when we simplify this, we can rewrite these square roots or roots as fractional exponents. So pi is on the outside, so you can really put pi on top, or sorry, pi is on bottom. So it's on the outside, and then in here we're going to have 500 raised to the 3/2 and over pi to the 3/2. I wrote that backwards. Nice. 2/3. I knew it was a third. And this would be 2/3 as well. So that would be 3 over 3. So 1 minus 2/3. 3 over 3 is 1/3. All right, there we go. Fix that. So this is actually 1/3. So I have 500 to the 2/3 over pi. Oh, it's a positive 1/3. So positive. So we can put that pi to the 1/3 on top. So those are both thirds. So this is 1,000 is still on top for our h over 500 is being squared, and we have pi, and they're both under the cube root. So okay, so here on this next one, we're going to find a point on a parabola. So we can go ahead and graph this. So we could plug in x's and find y's. That's fine, or plug in y's and find x's. So to do that, I mean, you can just square root this, right? And plus or minus. So I could plug in x's like 0 and get 0. Plug in 2, I would get 2 and negative 2, because when I square root 4, I get 2. And then I could plug in 8 and get square root 16, so that'd be negative 4 and positive 4. Okay, or I could solve this for x, just divide by 2, and then I could divide by 2, and then I could just do the same thing. I could plug in y values, so plug in 0, I still get 0 for x. I plug in 1, I get 1/2 for x. I plug in 2, I get 2. So the same thing. So I have this parabola, sideways parabola, because it's a square root function. So 0, 0, 2, 2, and negative 2. 3, 4, 5, 6, 7, 8, 1, 2 for 4, and negative 4. So it looks something like this. And then I have this point, 1, 4. And what I'm trying to do is I'm trying to find what point along this parabola is the closest to this point 1, 4. So I'm looking at the distance between 2 points. So I need the distance formula, which is square root of x squared x2 minus x1, square that, and then I add the distance, or the difference between y2 minus y1. Well, I have one of these points, right? They give me 1.14, but I don't have the second point. So there's some random point on here. I'm just going to call x and call it y, because that's what I'm trying to figure out what those numbers are. So I'm just going to leave one x as x, and they give me the y of that point, and leave that y as just y. And I'm taking the square root of this because I want to minimize this. So I need to take the derivative of that. Well, the derivative of this is really hard because we have the square root in there, and it's actually, raised to the half. And I got to take that in front. I got to drop that power. Then I have to do chain rule of all this, and doing chain rule the inside of this, I'm going to have to do chain rule again. That is a squared, and that is a squared. Okay, so it's going to be really tough. Well, if I'm trying to minimize the distance, whatever the distance of this is, then if I just square that, so if I square that distance, isn't that still going to be the smallest one, right? So if here, say this is 5, this distance of 5, and this point over here is a distance of 8. Well, if I square both of those, 25 and 64, isn't this still the smallest one, right? So if I square both sides of the distance formula, the minimized, the smallest amount of distance is still going to be the same. Okay, so to get rid of that squared, we're just going to square that, both of these, to get rid of that root. So then we're just going to let the distance squared be the same as our distance to this point. So we're just going to let that equal f of x, or f of y, because we're going to solve in terms of x. We want this because we have two variables. So we need to make it into one variable. So if I solve this equation in terms of x, which is easier to solve for, then I can replace this x with y squared over 2. Which is just 1/2 y squared. And so then, now I can go ahead and derive this, which is a lot easier now. I mean, I'm still going to have to do chain rule, but it's a lot easier. And we'll just let this be f of y. So d squared is equal to f of y. And I do y because it's in terms of y here. All right? So now when I derive this, it's a lot easier to derive. I still have to do chain rule because I have a function raised to a power. So we leave the inside the same, we drop the power, and then we times by the derivative of the inside. Well, the derivative of the inside is 2 times negative 1/2, which is just negative 1, and we have dropped the power, so we just get negative y here. So we can simplify that to negative 2y, parentheses, 1 minus 1/2 y squared, which we can distribute that negative 2y to the inside, and we get positive y cubed here. And now I have to take chain rule of this one, which is to drop the power. But when I take the derivative inside, it's really easy. It's just negative 1, right? And so then we're adding that. We can take negative 2 and distribute the negative 2. So really it's just negative 8 and a positive y. I'll put the positive y in front and negative 8 at the end. Okay, and then I can combine these y's here. So we get y cubed minus y minus 8. And then we're going to set that equal to 0, right? Because to minimize or maximize, we always set it equal to 0. And of course, it didn't multiply correctly because when I distribute this, I get negative 8 and negative 2y, which becomes a positive 2y. So this is really positive 2y. You're probably wondering that. So this y's cancel out. So this is gone. And then so we can solve this. We can add 8 to both sides, and we can just take the cube root. And the cube root of 8 is 2. So y is equal to 2. Now I can go ahead and plug that in. And so that is 4 over 2. My x is equal to 2. So now my x and my y are both 2. So I have this point 2, 2, and that's the closest point. Okay, so then we also have these other things that we maximize or minimize, the cost or the maximize profit or whatever. So cost function is just how much it costs of producing a certain amount of items. So that's usually just C of X. The marginal cost, that's the rate of change of the cost. So how much the cost is changing. And so that's our derivative of the cost function. And then we have revenue. Revenue is how much, how many items we make and the price that it costs to make them, right? Or how much we're charging. So how many items we make and the price per item. And then our profit is just taking that revenue, how much we're making from each product minus how much it cost us to produce that amount of items. Okay, so that's the profit. So depending on the question, we might be maximizing profit, so taking the derivative of the profit. We might be maximizing our revenue or minimizing, probably not minimizing these ones. So we'll be taking the derivative of those. Or we might be trying to minimize the marginal cost, right, to lower that. Or we might be minimizing the um, cost function, so taking the derivative of that, which is the marginal.